Okay, this question asks about the depth of the center of pressure on the triangular vertical plate. Show, looks like there's an N missing, if the apex is 1 meter below the surface. So there's an image here, and let's take a look at that image. Number 676. Okay, here's a drawing for number 6, and one of the things that is important about this is it asks for the center of pressure. Now, this relies on us knowing what the center of pressure is. So the center of pressure is essentially the point at which a point force would act. If you took the average pressure and you said, okay, that represents a point force acting over the area, where would that force be acting? So this is, let's define it, this is the point at which a point force or resultant force acts on the area. So we know that underwater here, that the pressure at this point, let's say if we're plotting it, the pressure is some value, but we know that as we go down into the water, that pressure increases with depth. And we know the slope of that is, the slope of this line, if this is y, is equal to rho times g, because we know that the pressure as a function of y equals rho times g times y. And y is measured from this point here. So the slope, the change in pressure with y is this rho times g, so that's the slope here of this guy. So we know that the average pressure is something, it's actually the pressure, the shortcut that we know is the average pressure is going to be equal to the pressure evaluated at the centroid. So a pressure evaluated at yc, which is equal to rho times g times the distance from this top surface to the centroid of this, the geometric centroid of this triangle, which we know is a third from the bottom. Well, we know that by looking it up in a table, that this is 1/3 times the height of this thing, or this is 0.4 here, that means this is 0.8, and what I'm doing is I'm dividing this number up. So this is yc, and so this is rho times g times 1 plus 0.8 times 1.8 meters is the average pressure. Now that average pressure produces, we can say that is represents a resultant force that acts over the area of that triangle. And the center of pressure is the location of R, where R actually acts on that triangle. Now it turns out, you could probably convince yourself this, but it turns out that this is R is acting below the centroid of this triangle at what we call the center of pressure. So y sub p, the center of pressure. And we have to calculate that. And this is always a tricky calculation because well, at least as I see it, the equations in the fundamentals of engineering reference are really, really confusing on this point. And I'm going to actually go to those equations in a second. Let's first calculate what the numerical value of this average pressure. It is equal to 1,000 kilograms per meter cubed times 9.8 meters per second squared times 1.8. That's roughly, what is that, 10,000, almost 10,000 times 2, almost 20,000, we'll call it 18,000 newtons per meter squared. This is my guess. Damn it. Let's do it with a calculator. Oh my gosh. So I've written the calculator answer here. The average pressure is 17,640 newtons per meter squared. Okay, that's the average pressure. We're really, though, asked to find the center of pressure, so the point at which the force is acting. I guess we didn't really need to calculate that average pressure. Let's see, how do we calculate the center of pressure? I really only know one way to do it myself. There may be shortcuts, but what I do is I first find that actual resultant force. I've got now the center of, or I've got the pressure, the average pressure, and I can compute a resultant force from that using this equation, knowing the area, so I can compute R. And then what I do is I basically set up a balance of the moments that force kind of causes this thing to want to rotate, and that gives us kind of a moment balance against the water that's submerged underneath the surface, and that leads to this equation here that I've derived before in class. I hope you all remember or somehow recognize it. It is that the yp minus yc is equal to the moment of inertia about the centroid divided by yc times the area. So essentially what you're looking for in this problem is this value right here. So we know yc from the page before is 1.8 meters. We can compute the area, 1/2 the base, I don't recall the base, 0.8 meters. 1/2 0.8 meters times the height, which is 1.2 meters. And IC for the centroid of a triangle is going to equal, let's look that up together because that's a bit confusing, this IC value. So we want to know the moment of inertia about the centroid for an isosceles triangle, for which we know the base and the height. Okay, let's go look that up. We're going to go to our FE materials. And I'm going to go to these numbers here. And here we have the values. They're not easy to read. Let me rotate this. Okay, so here, let's pick a triangle like this, and we want the moment of inertia about the centroid. And notice that we have these confusing set of values here, IXC, IYC. So the moment of inertia about the x-axis, but now about the centroid. So the one that we want is actually this one up here. Now, how do we know we want this one and not the other one? Well, if you can poke around in the pages ahead. It's not easy to decipher it. The way I decipher it is I say to myself, okay, what is the inertia? What is the real inertia about this centroid? Say we're trying to rotate this. Does it seem to be resisting with the base cubed, or is it with the height cubed? Imagine that this was a very high triangle, and you're rotating it about this x-axis or about the centroid. You can convince yourself that as the h gets really large, that is going to be the controlling factor, not the base. So here is where you could convince yourself that this is the formula to use, not this one down here. So the IC is equal to, base times the height cubed over 36. Base times the height cubed over 36. Okay, you can plug all these values in here and solve for YP. Let's go ahead and do that real quick. So YP is equal to YC, 1.8 meters, plus base times height cubed over 36. I'm just going to plug some of these values in. YC is 1.8 meters. The area is 1/2 the base times the height. And you notice here that some of these terms are going to drop out. This is going to be squared here. And 1/2 on the bottom, that's going to turn this into 18. Okay, so 18 over 1.8 is going to be 10. So this equals 10 times h squared. Yeah, that was pretty simple. 10 times h squared. H is, in our case, 1.2. 1.8 meters plus 10 times 1.2 meters squared. This thing squared, 1.2 squared is, what is that? 1.44 times 10 is 14.4. That doesn't make any sense. YP cannot possibly be 14.4 meters. 18 meters squared dividing this out. What did I do wrong? Oh, I see. This is what I did wrong. This is over 18. This over here equals h squared over 1.8 times 18. I wish I knew what that value was. Okay, so let's rewrite this. So this term is h squared over 1.8 meters times 18. This is equal to, this value is 1.2. So we have 1.2 over 1 squared over 1.8 times 18. Okay, that's more like it. I see. So this is going to be, this is going to be something small like 0.05. Let's try it. 0.2 squared. I'm using a calculator. 18. Oh, 0.04. So this is equal to 1.8 meters plus 0.04 meters. And so we end up with YP equal to 18.04 meters. Wow, that was a lot of, no, that's not right. That was a lot of work for a very little gain, it seems to me, equals 1.84 meters. YP. So that is, it looks like it's even, what is that, 10%? 1%, 2%, 2%. Not very much different. You know, kind of in engineering terms, you might even call it the same thing. So there you have it. That's how you compute the center of pressure.